When all of the development of BJTs and FETs was taking place, there was also some research and development taking place as it pertained to those individuals that were infatuated with higher power applications for solid state semiconductor devices. And thus was the birth of thyristors. I think you're all familiar with the spokesperson for the Thyristors, Suzanne Summers. Well, I'm the spokesperson, Chuck Norris, for the Thyristors.
I'm not sure. I don't know. I don't want to stay up late.
Chuck will kick your butt for telling him that, Chuck Norris, yeah. Now, Suzanne Summers was the spokesperson for the Thyristors. I'm the spokesperson for the Thyristors. Upon successful completion of this chapter, you're going to be able to identify common types of thyristors, describe how an SCR, triac, or diac operate in a circuit, draw and label the schematic symbols for an SCR, triac, and a diac, identify circuit applications for the different types of thyristors, identify the packaging used with the different types of thyristors, test thyristors using an ohm meter. That's something that all of you could do. SCRs, silicon-controlled rectifiers, are the best known of the thyristors. And again, they're referred to as SCRs. Hate to do this to you folks, but this is just how it is in the world of solid-state semiconductors. We have 3 terminal device and different names for the leads. Now we're back to anode and cathode, that all of you understand, right? And gate, which you understand. Now these SCRs are primarily used as switches. Controls current in only one direction. Why only one direction? Because it's got an anode, a cathode, and a gate. So it's going to be like a diode that could be turned on, if you will. But it's still going to allow current to only flow in that one direction. Now you can do the same thing with a power transistor, but that power transistor would require 10 times the trigger signal of an SCR to control the same amount of current. An SCR is constructed of 4 alternately doped semiconductor layers made from silicon by the diffusion or the diffusion alloy method. 3 junctions, not 2, not 1, but 3 junctions are going to be formed. And this is kind of sort of what it would look like if you were an artist. Depiction. Here we have a P layer where we attach our anode to. We have an N layer, another P layer that we connect our gate to, and then another N layer that we connect our cathode to. Cathode, anode, and gate. This is kind of sort of the electrical equivalency of it using transistors. And we know that current flows negative to positive, so our primary current path is going to be cathode to anode. And the gate is going to control whether or not that current flows or not. But I think you can clearly see how the anode must be made positive with respect to the cathode in order for this to function. This is what the schematic diagram looks like. It looks like a diode, except off the cathode it's got this little leg with a G attached to it. G for gate, A for anode, K for cathode. K for cathode. SCRs are used primarily to control the application of DC and AC power to various types of loads. Could be used as switches to open or close circuits. SCRs made Saturday Night Fever possible. All of the lights flashing in a discotheque typically are brought to you by SCRs. A lot of SCRs used in special effect lighting. because the voltage that we apply to that gate can control the sequence, the pulsing of the lights for different effects. So a small gate current can control a large load current. That's why we have these. But again, keep in mind with an SCR, it's really DC, right? Because we could put AC into this thing, but how much is going to get out of it? Only half of it, and that half is going to be negative to positive, so it's going to be DC, pulsating DC. So AC cannot make it through an SCR. But for a lot of effects, doesn't matter. If you're in a discotheque and you simply want to make lights pulse and blink, doesn't matter. It's an incandescent light, flashing to the beat of the music. It's no big deal, doesn't matter. Even for some dimmer switches, right? Doesn't matter. DC, your whole effect is trying to dim the incandescent light bulb. So it doesn't matter. To deal with the problem of not being able to use this on AC loads, they developed what's known as a triac. This is an acronym for triode AC semiconductor, triac. A triac conducts both directions of AC current flow. The positive alternation as well as the negative alternation. Has the same switching characteristics as SCRs. It's just bidirectional, right? It's equivalent to two SCRs connected in parallel with each other back to back. And it's a new component, so guess what? We've got some new lead names. But again, they did this really to make it easier for us. If we have an anode and cathode, as soon as I say anode and cathode, you assume polarity, right? Does one of these triacs have polarity associated with it? No, it'll conduct positive or negative. So what they've done now is they've called it MT1, main terminal 1, main terminal 2, and a gate. And literally inside it's the equivalent of, there's one SCR with the cathode on the top. Here's another SCR with the cathode on the bottom. So this one will conduct current flowing negative to positive. This will conduct flowing positive to negative on this side. Triac construction, 4-layered NP device in parallel with a PN device, designed to respond to a gating current through a single gate. It's not equally sensitive to the gate current flowing in opposite directions. This is a problem for some applications because it's not equal. Advantages and disadvantages of SCRs and triacs. I want you folks to strap yourselves in and hang on for this. These are some big numbers. Current ratings for triacs go all the way up to 25 amps. That means just about anything in your home you can control with a triac. I mean, the biggest outlet in your home, other than like an appliance that's hardwired to your box, is going to be 20 amps. So anything that you could buy consumer and plug it in a wall can be controlled with a triac. SCRs, 1,400 amps. So you understand that size matters. So if you have an SCR that can control up to 1,400 amps, one would assume that it's quite heavy and it's quite big. Does anybody know the maximum current that goes to a typical residential connection, your home? Maximum current that goes to your home? How many amps? Do you know how many? Some might. An older home might. Most of the newer homes, the standard is 200 amp box. So with a SCR that's rated at 1,400 amps, you could control 7 homes with no moving parts. That'd be pretty cool. Yeah, with no moving parts. You wouldn't even hear a ka-chunk. You just silence. Voltage ratings. Triacs can maximum of 500 volts. That again is pretty much anything residential. The highest you go residential is 240. What's that?
So then, since they handle so much current and voltage, they most likely be used for businesses. SCRs?
Well, triax typically is going to be, it could be commercial residential. So any controlling you're doing in a home appliance typically is going to use a triac for AC.
And then SCs would be, SCRs would be business.
High-end applications. SCR's maximum rating is 2,600 volts. 2,600 volts. So for some of these applications, I mean, think about it. Even like at a train, a rail yard where they build trains, and you switch the tracks. I mean, if you've ever played around with model trains are based on the real thing. So at a freight yard, they've got literally train tracks that will automatically switch. Well, you've got big motors that are moving those. How do you control those motors? You could use SCRs. It's a DC motor to move the track, to switch tracks. One of my favorite things to do, not like in the world, but kind of fun if I'm bringing somebody that's not acclimated to aviation, is take them on an airplane ride at night in my airplane. And Bremerton Airport, it's a big airport. I don't know if you've ever driven by over there. It's a big airport. You can land a 737 out of Bremerton Airport. It's a long runway. Has what's known as pilot control lighting. So what I can do is when I'm flying, and normally the lights shut themselves down after a certain amount of time. So what I'll do is I'll fly over there, and then on instruments, I'll start the approach to the runway. So I'm coming down, coming down, coming down, and it's just black in front of you. You don't see anything. And then there's a frequency that I could dial in, and then typically click. If I click 3 times, it brings them up low intensity. If I click 5 times on my microphone, it brings them up in high intensity. So all of a sudden, you're coming down, and I'm like, you know, whoever's with me, I'm like, check this out. Click, 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 click. And all of a sudden, poof, here's this huge runway, you know, with the chaser lights and everything. And I just controlled that wirelessly through my transmitter. The receiver picked it up. Once the receiver processed it, it's probably telling a whole bunch of triacs and SCRs to go ahead and turn on the entire airport lighting in one fell swoop. It's kind of cool. Like, how'd you do that? Secret. No. Triacs and SCRs. That's how you do it. Frequency of triacs, 50 to 400 hertz. Again, this covers everything for typical commercial residential use for power, right? 50 hertz is used in Europe. 60 hertz is used here. Who uses 400 hertz? Should be review. I talked about this last quarter. There's 3 flavors of power out there, electric power. 50 hertz Europe, 60 hertz North America. Who uses 400 hertz? Give you a hint, it was something I was just talking about. Airlines. If you get on board an airliner down at SeaTac Airport, that power on board the airplane is 400 hertz. They started using that because of the quality of the AC power in the past. And when avionics were developed, they just continued to develop them with 400 hertz. So it's actually, next time you're on an airplane, think about that when a captain gets on and he clicks his mic. You know, this is the captain speaking, from the flight deck. Where else would the captain be? It's the captain from the forward lavatory communicating with all of you. But when he keys the mic, he or she keys the mic, you'll hear a tone about like that. That's the 400 hertz noise. If any of you play around with audio equipment, music, you'll hear that hum, that 60 hertz hum. On aircraft, it's a higher frequency. So anyway, triacs can be used basically for any power applications that we use. 50 hertz, 60 hertz, 400 hertz. By the way, when you're measuring AC with your fluke meter, these are the only 3 frequencies that your AC setting is really designed to measure. Up above about 1,000 hertz, the accuracy of measuring AC with a handheld DMM. If you're at 2,000 hertz and you try measuring frequency or voltage, chances are it's going to be erroneous. That's why we have to use the oscilloscope. SCRs can handle all the way up to 30,000 hertz. Triacs, although they're very good for AC, they have difficulty switching power to inductive loads. Remember induction? We talked about it in the past, an inductive kick. What would be an example of an inductive load? What's that? A motor. A big motor. Motor in your washing machine, motor in your dryer. Motor in, I've got a spa at home. It's got two big motors in it to turn the pump, make the water come out of the jets. Okay? Those are controlled, I know, because as soon as I got it, I tore the thing apart to look in there. How's this thing put together? It uses relays. It's not using solid state components. It's using little relays that click on, click off. Because for a big inductive load, I mean, some of those motors, you know, are huge at my spa, move a lot of water. So triacs have difficulty with that. But for smaller applications, you can use a triac on an inductive load. Bidirectional or two-directional trigger diodes are used in triac circuits because they have non-symmetrical triggering characteristics. The most frequently used triggering device is going to be the diac, or what's known as the diode AC. Diode AC. A diac construction is 3 alternately doped layers. The doping concentration around both junctions is going to be equal. Leads are only attached to the outer layers. It's going to be packaged like a standard PN junction diode. So you're going to have to look up the part number to make sure that it's not a standard diode, that indeed it is a diac, diode AC. This is the artist's depiction of the layers. Down at the bottom here is a schematic symbol for a diac. Diac has all the same effect on current regardless of the direction of flow. One junction's forward biased, the other's reverse biased. Performs as if it contained 2 PN junction diodes connected in series back to back. So again, we're going to use this diac with a triac so we get symmetrical triggering characteristics. Diacs most commonly used in conjunction with triacs to provide that full wave control of the AC signal. Useful for controlling lamps, incandescent lamps, heaters, and the speeds of small motors. Not big motors, because big motors have large inductive properties that we're just not going to be effective in controlling it. Thyristors can be tested with a commercial test equipment or an ohm meter. Refer to the operator manual for proper settings and readings when using commercial test equipment. The ohm meter can detect the majority of defective thyristors. Basically, you're looking at for opens and shorts. It cannot detect marginal or voltage sensitive devices. In order for you to do that, for you to test that, you're going to have to build your labs. And in your labs, they show you test circuits. Basically, if you look up the data sheet for a thyristor from the manufacturer, they're typically going to show you how to build a little test circuit so that you can evaluate that SCR or that thyristor. And that's how most of these lab books, the authors of these lab books, get the test procedure. They just simply rip off a data sheet and say, hey, build this. It's one of the reasons you really want to do these labs this quarter, because you're never going to have time to go back. You're not, trust me, you're not going to be able to enter any type of a cultural renaissance when you're out in industry making money saying, oh, it's a Friday afternoon, I got some free time. I think I'm going to do that thyristor lab. It just doesn't happen. You get your first job paid as a technician, you're going to get paid to fix stuff. You're not going to have time to go back and do your ELEC 120 labs over again. So basically what I'm saying is just make sure you really go through them legitimately and have some fun with them, because this is your chance to really see these individual components working in an isolated condition. So when you get out into industry, as soon as you see a problem, you're going to say, I've seen that before. I saw that in a lab when I was doing the thyristor lab. In summary, thyristors include SCRs, which is really the most popular thyristor, triacs, diacs. SCRs control current in one direction by a positive signal gate. They're turned off by reducing the anode to cathode voltage to 0. Used to control current in both AC and DC voltages. Schematic symbol, anode, cathode, and a gate coming off the cathode. Can handle up to 1400 amps, 2600 volts, 30,000 hertz. Is this all SCRs or just some of them? Just some of them. You got to look at the data sheet. You might have some SCRs that can only handle a half an amp, 10 volts at 60 hertz. So make sure you look at the data sheet. If you actually had, again, if you had a, I wouldn't even want one. We'd need like a little crane, one of those engine hoists probably, 1400 amps. It's huge. Be a heavy component. Triacs, bidirectional triode thyristors, control current in either direction by either a positive or negative gate signal. The leads are known as MT1, MT2, and the gate. Can handle up to 25 amps, not 2500. 25 amps, 500 volts, 400 hertz. Pretty much can control anything in your house. Requires the use of a diac because they have non-symmetrical triggering characteristics. Diacs are bidirectional triggering diodes. It's like two diodes back to back, opposite polarities. Most used as triggering devices for triacs. Basically, you got to test and evaluate the performance of all of these devices using nothing more than a commercial transistor tester if you have access to one, or an ohm meter, which will show you the majority of opens and shorts. Any questions on anything we covered in thyristors? All right, that's all I have for lecture this evening.